Hello, this is Team Turbo presenting Webot 2, a 1 to 10 scale autonomous car built for the auto race competition in Busan, where vehicles must complete a mission based track fully autonomously. The presentation briefly covers the motivation for autonomous vehicles, then the robot platform, sensor fusion, mission logic, individual track missions, and finally, potential applications of this architecture. What is autonomous driving? Autonomous driving means a vehicle handles steering, braking, and acceleration without continuous human input, by using sensors to perceive the environment and software to select safe actions in real time. Webot 2 is a 1 to 10 electric car with an onboard computer, motor controller, camera, LiDAR, and IMU running under ROS, forming a compact but realistic testbed for autonomous driving. The Brains, an Intel NUC with Ubuntu and ROS 1, runs all perception and control nodes, while a WESC motor driver drives the BLDC motor and steering servo and returns speed and power feedback. The ELP wide-angle camera provides images for lanes, crosswalks, signs, and parking. The RP LiDAR S1 supplies 2D range data for cones, barriers, tunnels, and roundabouts. And the 9 degree of freedom IMU stabilizes orientation estimation. The track is divided into 8 missions: zone, crosswalk, cone, lane decision, roundabout, barrier, tunnel, and parking, and the state machine switches between them, with lane following as the default behavior. Lane following crops the road region, warps it to a bird's eye view, detects lane pixels, fits a center line, and uses the Stanley controller to keep the vehicle near the lane center. This flowchart summarizes the 30 Hz loop: read image, warp, extract lane region of interest, apply HSV filtering, detect lanes with sliding windows, compute errors, then output steering and speed plus debug visualization. In the zone mission, road color in the bird's eye image sets speed. Red zones slow down and blue zones speed up. In the crosswalk mission, a stripe pattern triggers a controlled stop and short wait before continuing. For cones and the tunnel, LiDAR points in front are split into left and right boundaries. A smoothed midpoint path forms a virtual centerline, and pure pursuit steers the car between the cones and through the tunnel. The lane decision mission crops a region with the direction sign and performs template matching against left and right images. The best match sets the path, and the controller follows only that lane branch. In the roundabout, a front LiDAR sector is monitored. If a vehicle is detected, the car waits at the yield line, and only when the sector stays clear long enough does it enter and follow the lane through. The barrier mission uses front LiDAR distance to stop when the lane is blocked and continue when it becomes clear. The parking mission triggers on a white line and then executes a time-based sequence of steering and speed to park in the box. The next slide will show a short video of all missions executed in sequence. future applications. The same state-based design can be applied to sidewalk delivery robots, where missions such as lane keeping, speed zones, crossings, obstacle handling, and docking appear in a more complex urban setting. As a product, this type of system fits B2B logistic and delivery services and B2G smart city pilots, aiming to reduce last mile labor costs and increase reliability in dense urban areas. The system remains sensitive to lighting and track appearance, relies on hand-tuned rule-based state machines, and only models other actors through simple distance thresholds rather than richer semantic understanding. Future improvements include learning-based perception, tighter camera lidar fusion, and more adaptive decision making, so the framework generalizes beyond a single track layout to more realistic environments. Overall, Weebot 2 demonstrates that a state-based perception and control framework can be realized on a small platform while capturing key aspects of real autonomous driving. Thank you for listening.